Hi, my name is Ethan Willingham, and this is my final individual project for Cyber 332. My instructor name is Jennifer Grant, and before we get started, as a disclaimer, this is solely for educational purposes, and I would not be liable for any damages that could be caused using these demonstrations. I'm but a student. So what my project will be on is quantum computers, specifically Neven's law and Shor's algorithm, the relationship between them, and their implications on the future of cybersecurity. We'll kind of go into the power behind quantum computing, what it allows one to do when using certain algorithms like Shor's algorithm, and the potential threats it poses to current encryption systems. So let's start off by talking about Neven's law, and in order to understand Neven's law, we need to talk about Moore's law. Moore's law states that computing power will double approximately every 2 years. This has held true for many years, since 1965, and the person who invented that was Gordon Moore. He was the co-founder of Intel. However, there is not an equivalent for quantum computers, or at least there was not until 2019, when a man named Hartmut Neven put forth his law into existence. Now, he was the head of AI at Google at the time. He was behind the team that created the first quantum computer to accomplish quantum supremacy, meaning that it achieved a task faster than any classical computer can. And Neven's law states that every 2 years, quantum computers will grow in processing power at a doubly exponential rate. The reason for this is that every time a qubit is added to the quantum CPU, it doubles the power of the quantum CPU. So when I add one more qubit to a 100 qubit quantum CPU, it doubles the power of that computer. At the same time, the number of qubits that are being added is also being doubled every 2 years. So you can imagine quantum computers are going to ramp up at a fast pace if this person is correct about their assumptions and their law. Now let's move over to talking about Shor's algorithm. So this algorithm is made by a man named Peter Shor in 1994. This algorithm is designed specifically to factor large prime numbers, which, if you aren't aware, is the main mechanism behind most encryption technologies today. RSA encryption, as well as other popular encryption techniques. Classic computers have a very hard time factoring large prime numbers, and that's why these numbers are used as keys on either end of encryption methods that we use today. However, this algorithm, which can only be ran efficiently on a quantum computer, can break that encryption. So this, in essence, is a threat to current encryption systems because it can solve the problems that are considered impossible for classical computers. Now, what's required for this algorithm to break current encryption techniques is a quantum computer that is scaled at a much larger size. It is estimated that a quantum computer needs somewhere between between 1 million and 10 million qubits for it to be able to break, let's say, the encryption that is currently on your email account. All right, so instead of having a direct demonstration here for my project, which would be rather difficult with such a theoretical subject, instead what I'll do is point towards some resources and kind of talk about what some of the leaders in the community are talking about, both in the private and the government sectors. So first, what I think is a good idea is to kind of wrap our heads around what we mean by doubly exponential. If you're a math whiz, you already know. If not, this is a great example here to show you what that really means. So the sequence of numbers moving at a doubly exponential pace would start at 0 being your first number, and then 2 being your second number, 5 being your third number, 277 being your fourth, and then just the fifth number in the sequence moving at a doubly exponential rate is 5,195,977. So it's worrisome to think that a new technology can grow this fast, and it's easy to see how maybe this will pop up before we are really ready for it. Moving over to IBM's website, which is one of the leaders in the community, the quantum computing community, we can see the different years they have listed here. This is their roadmap with as it pertains to their quantum computers. Their first computer in 2019 had 27 qubits. They called it the Falcon. And then moving into 2020, they had one with 65 qubits. 2021, they had one with 127 qubits. And so on, moving into 433 qubits in 22, and then this year being 2023, they're expected to have a computer with almost 1,200 qubits. Now you may be asking yourself, this is a bit faster than what was previously stated, and you'd be right. It is moving even faster than Neven predicted in 2019. These are more than doubling in the number of qubits per year. And if it continues at this pace, then we're looking at something a bit faster than what was expected by Neven. To get a better idea of that, there's a beautiful graph here. I'll leave the link to it. But I wanted to include this because it's a great visual representation of the prediction of what may or may not happen here. Basically, the orange line here is the number of qubits in a quantum computer that is predicted that will be needed in order to run Shor's algorithm and to break classical encryption. Over the years, that prediction has moved down as new technologies have been invented. And then this blue line here is IBM's the roadmap that I just showed you, and how many qubits they have in their quantum computers, and then, or rather, the roadmap is the beginning of it's what they've already done, and then as you can see from this point forward, this is the extrapolation of what's expected in the future. So as you can see, current estimates put it as early as 2031, where we are 100% going to need all of our encryption techniques to be moved over to quantum safe encryption. And then a more realistic idea would be around 2035, 2036. And of course, this graph moves on further into 2040, 2045. And then one last thing I wanted to mention was Grover's algorithm. It can be concerning to learn all these things about quantum computers, and maybe you think to yourself, this is a bad thing, but let's keep in mind it does other things as well, such as using Grover's algorithm, which uses something called quantum parallelism Grover's algorithm is a quantum search algorithm that can find a specific item in an unsorted database quadratically faster than classical algorithms. So, better said, it will increase the efficiency in the big data sector significantly. So there are good things that come from Grover's that come from quantum computers. One being Grover's algorithm and its application in data science. Now we'll move over to the NSA's website. NSA's website, it says right here, use of a quantum computer could be devastating to NSS and our nation, especially in cases where such information needs to be protected for many decades. Keep that in mind. It needs to be protected for many decades. Now, the NSA is saying devastating to NSS and our nation. That is some pretty strong language. But they're right. Our world today, at least in some more privileged countries, is based very much heavily on computer technology and therefore encryption. All right, moving on to the PowerPoint part of my presentation. Why should I care? One phrase: store now, decrypt later. Bad actors are intercepting messages and data today, and they are keeping it. Eventually, they will be in a world where there will be quantum computers that can decrypt these messages and data, and they'll just wait until they can decrypt it, and then they'll decrypt it. So For instance, research data or intelligence information that our government possesses or our private companies possess. When they send that over the wire, those things are being kept by bad actors, especially the data that will be still valuable in 10 years. But that doesn't directly affect the individuals. So, why should I care? Well, our information is also sent over the wire, such as our social security number, which can be used in identity theft, which would probably be the number one reason why you should care. Massive loans can get taken out in your name, and there's nothing you can do about it if enough of your private information is taken. So get out there and tell people about quantum computers and the threat that they pose. The subject is just too complicated and too big for one person to make an impact. But spreading the word, I think, is one of the greatest things that an individual can do to help with the future of humanity as it pertains to quantum computers, after other ones as well. So in conclusion, the potential impact of quantum computing on our digital security is of critical concern, and it must be taken seriously. Although it may take many years before quantum computers can effectively break our current encryption methods, the store now, decrypt later approach poses a significant threat to sensitive information such as passwords. So to address this, we need to let our fellow people know, and then also the researchers that are already out there and the industry experts working on developing quantum resistant technology. They need funding, and I think spreading the word is probably the best thing that we can do as individuals to help. Thank you for listening to my project, and I hope you have a wonderful rest of your day.